Yes, how to do that.
We got functions, right? We got them on the side. If we did the auto bound, we could try to push it clear of the. I don't know. That's probably the school. We got functions on the side, right? And so I think how much of one the other is literally, only the possibility of that we probably survive and I
How does that happen?
so that was my surprise.
Okay, go ahead, hold up, put your hoodie on.
Okay, so by literally by Tuesday, they've gotten so moldy that they're melting. So like, I know a pumpkin is round, and it sits in a sort of round box. It's so funny because the bottoms have melted, and they're just like round circles on the floor. That's how moldy they got in 2 days. They were melting or wet.
That is disgusting. Hilarious. Did you get it out?
Yeah, we clean them like crazy. It's great. Those things long very awesome.
What was the function?
P of x is 11
X to the 11th?
minus 5x to the 4th plus 10x to the 3rd
5x to the 4th.
plus 10x to the 3rd
It's true.
plus 9.
Okay, so this was the problem, and what we'll find is very quickly is this is going to be a very easy one, okay? Because we're going to get into more complicated ones. This will be very easy. But to start off, what I'd like to do is really break this down, because when we get to the harder ones, this way of approaching them is going to be helpful for you. So what you want to do is, here's the key. You look at a function and you want to find the closed form rate of change function. The first question you ask yourself always, and I'll ask this in the next week, we're going to be asking this over and over again. What's the overall structure of this? What's the overall? Because all 4 of the rules that we've learned so far apply to this. But what's going to help get you started is to know what's the overall, what's the big picture of it, what's the structure of it. So what are the 4 rules we got? X to the n, right? C times gx, and say just basically fx plus gx. So is in the big picture, is this whole thing, is it something, is it x to a power? Is it a constant? Is it a constant times another function? Or is it the sum of functions? No, but in the big picture. In the big picture, in the structure of it. So I'm going to be a broken record this week. The whole structure of it, what is it? It's the sum, right? If you look at the whole big picture of it, it's the sum and difference. Okay, so that's what we apply first. And what is that rule? That if you have a function that is the sum or difference of other functions and you want the closed form rate of change, the rule says, Kyle. So the question is, what is the rate of change of a sum of functions? What's that?
Isn't it the rate of function a with respect to x?
Not quite. If we have a sum of functions and we want the rate of change of that sum of functions, what does the rule say? So it's the sum of the rates. So we can call this one f of x. Now like I said, you're not going to do this, but it's the idea of identifying So now to find the rate of change of p with respect to x, It's going to be the rate of change of f with respect to x plus the rate of change of g with respect to x. So that's applying the first rule, which is sum. Okay, now let's look at f. So here, what's the big picture of that? Is it 1, 2, 3, or 4? It's 1. Okay, which says that we can do 11x to the 10th. Okay, here we go. What's the big picture of g? 1, 2, 3, or 4? It's 3. It's a constant multiple times a function. So we could rewrite this as, what's our constant multiple? It's actually negative 5. And we need a new function, so call it k of x. So if g is negative 5 times k, then the derivative of g is going to be negative 5 times the derivative or the rate of change of k. Which is, so then what's our k function? X to the nth. So this is going to be negative 20 x cubed. Alright, big picture of this. Or its structure of that. 1, 2, 3, or 4. It's 3 again. So it's going to be 10 times the rate of change of that function. Which is 1, 2, 3, or 4. That's 1. When you have x cubed, that's like number 1 here. So it'll be 10 times 3x squared. Okay? Then jx. 1, 2, 3, or 4. 2. Rate of change of 9? 0. So it's 11x to the 10th minus 20x cubed plus 30x squared. That's the rate of change of p with respect to x. So that's what we want to focus on. When we start, when you come to a finding, you want to find the closed form rate of change function, the first question you're always going to ask yourself is, what, because we're going to have lots of rules. Very quickly, we're going to have lots of rules. And so you're going to come to a function and you want to ask yourself, what's the structure of it, or what's the big picture of it? So we know in totality kind of what rule are we applying from the start. Because that will get you going on the right track. Questions on the homework? Very good. Okay, so we're going to add to our list of rules. Okay, before we do that, let's just summarize a little bit here. So, really, this is all about closed and open form. So, just as a review, write the rate of change of the function x to the n in open form and in closed form. Okay? See if you can do that. So, can you write the rate of change of x to the n in open form and in closed form? So who's first today? How about Isabella? Did you get open form? No? How about Reshma? Did you get open form? For x to the n. N x to the n minus 1. That's open for. Is that open form for this rate of change? Is that closed or open? That's closed, right? Our closed form is when we get a nice clean function that gives us exact rate of change. So open form. Megan, did you get open form? Oh, Ryan, go ahead.
X plus h to the n minus x to the n over h.
Thank you. Right? So make sure you know that the general formula for open form, and you can apply it to any given function. Right? So this is f of x plus h minus f of x over h. Okay? And so then Reshma gave us closed form, which we know this is our rule for the closed form for this type of function. Okay, this open form is an exact rate of change function or approximate? Okay, so what is the exact open, so rate of change in the exact rate of change function for x to the n in closed form? No, sorry, in open form. So I want the exact rate of change of x to the n in open form. Danny, what would that be?
It's the limit of the open form as h approaches 0.
Yep, that's it. Here's exact open form, exact rate of change in open form. To get it to be exact, we need to h get so like atomically small, so small that we have the exact rate of change function. And how do we read this right here? Oh no. How do we read that? What is that? Right there, Jessica.
The rate change for the function with respect to x.
Okay, and so we know what function that is, right? The rate of change of what function? Yeah, exactly. Yeah. So this is the rate of change of x to the n with respect to x. And so rate of change function so you've seen this word in the book, and I was using it a little bit this morning. Okay, it's derivative, okay? So rate of change function, so whenever you see derivative, immediately your mind says, I know what that is. What is it? The rate of change function of the given accumulation function, okay? So what about, so then exact in closed form? So we already have the closed form. Okay, so the column on the left is our open forms. Okay, those are open forms. So based on average rate of change is the first one, so it's an approximating rate of change. But then when we let h get very, very, very small, we get the exact rate of change function. And then on the right, we have our closed forms. And so that first one in the upper left-hand corner, that's our approximating rate of change function. And then the second row is our exact rate of change functions, whether it's open form or closed form. So what is our current quest here? Our current quest is rules for various functions to get closed form quickly. Okay, so we're developing rules for various types of functions so we can just write down an exact closed form quickly for rate of change. Okay, how are we going to do that? How are we going to find these closed forms? So I'm going to give you a new type of function. What's going to be our strategy in general, most of the time, to find the closed form? Allie.
Using the open form.
Use the open form. Remember class yesterday. Every time we came to a new rule, it was always about start with the open form. Okay? So the open form is, we can follow it. We can just basically write it down for any given function. And then we need to do a little work, right? A little algebra to see if we can find a closed form. Okay. Any questions on the overview here? Make sense? Okay, so let's do change the square root function. So our goal is to find a closed form for the rate of change of the square root function. You write down the first step. Go. You write down the first step. So Eric, can you tell me in general what our first step will be here in trying to find the closed form?
It's radical x plus h.
Okay.
Plus radical x over h.
Almost 99%. Just one small error. Minus, right? Okay. All right, and so then here's a heads up when we work through this. This is going to be helpful. Remember that a minus b times a plus b is a squared minus b squared. Okay, remember that little rule? That's going to help us in this one. So he got it. The rate of change in open form, radical x plus h minus radical x over h. And so we're going to use this, because they're both square roots, it would be nice if they were both squared, so the square roots would go away, right? So from that, this little formula over here, so if we could get both of these to be squared, the radicals would be gone, right? So we have a minus b, so what are we going to multiply by?
A plus B.
Yep, but if we do it to the top, we got to do it to the bottom too. So we're not changing the value of this because we're multiplying by 1. And so the reason we did this is we're going to use this red formula on the side, and it's going to simplify the numerator greatly. So what will the numerator simplify to? How about Jason?
Will be x plus h plus x
Almost, also 99%.
minus.
Minus, right. So it'd be, yeah, so it's a squared minus b squared. So it'll be x plus h minus x. And then the denominator is just the same as it was. Okay, so the numerator becomes just h. And so, like we've seen before, we need that h in the denominator to go away, right? So now h over h is 1, and it goes away. And then once we do that, then we can say we want h to be essentially very, very small. And we get 1 over 2 radical x. Okay, do all the steps of that make sense? We found a closed form rate of change function for radical x. Okay, so what I want to show you here is how could we also write remember this notation means we use that the ratio without the limit, so it is essentially equal to this for small values of h. So if I were to use this notation, this implies, this is derivative notation, it implies exact closed form. So we can say equals. So it equals 1 over 2 radical x. What exponent does x have if it's 1 over the square root? David?
X is the 1/2.
X is this 1/2 times x to the 1/2. X to the 1/2 in the denominator or the numerator?
X of the negative.
Okay, so yeah, so if we want to just have 1 power of x here, since x is in the denominator, it'll be negative, so 1/2 x to the negative 1/2. And what was the original function as an exponent? X to the 1/2. Notice anything? What's that?
The power rule.
Say more. Allie says it's the power rule.
You bring the 1/2 to the front and then you subtract n minus 1.
Remember our power rule said that if we had x to the n, the closed form rate of change function was n x to the n minus 1. So, n, and what's 1/2 minus 1? Negative 1/2. So radicals, when changed to their exponents, still follow our power rule. So, few practice problems. So I want you to find closed form for all of these. Find the closed form, rate of change for these. These are separate. We can make them. We could sum them up, right? It doesn't matter. We could make it all one function and sum them, or we could just do them separate because that's generally the same thing. So when you have x to a power, it could be a negative, it can be a fraction, it can be a decimal. The power rule still applies. Okay, the power rule still applies. So how would we do x to the minus 3? Somebody new. Mason, want to try x to the minus 3? No. Okay, how about Megan?
Is it -3x to the -4?
Yep, you literally subtract 1. You don't make it 1 closer to 0. You literally subtract 1 every time. So if it's a negative, it's going to get further from 0. Okay? So -3, still minus 1 is -4. Okay, who wants to try the next one? Brian Kirk.
10.87x to the 9.87.
Yep. So whether it's decimal, negative, fraction, you literally follow the rule. Subtract the exponent by 1. Okay, Ben, how about the next one?
Well, first it would be x to the 4th.
So which is numerator, which is denominator?
That would be over, it's 5/4.
5/4, right?
So it'd be 5/4 x.
That's it. John Paul, last one.
0.1
Mm-hmm.
x to the negative 0.9.
Okay, do these make sense? Yep. Okay. But this one, this is just a very common. So square root is very common, and rather than change it to the power, write it in the power rule and then change it back, it's good to remember it in this form, right? Just remember it as 1 over 2 radical x. It's more convenient than doing all the switching to power and switching back, okay? But just know that it is still the power rule. Questions on that? Okay, so here's a brand new type of function, b to the x. So notice, what have we done so far? X to the n is what we have under our belts. That's when the input is the base. And we're raising it to some power. But the input value is the base. That's what we've done so far. Now, what's different about this? The input is the exponent. Totally different, okay? So students often confuse these. When the x is the input, when the exponent is the input, now we have something new. And so we want to work this out. So let's begin with what we begin with. So what are we going to do in this one? So how about Tony? How would we start if we're after a closed form for b to the x? How do you want to start? Yeah, what is it?
F, or rate of f of x
Okay. Rate of change of f with respect to x.
is equal to, I wanted power rule.
Well, but it's totally different. So that's the point. Power rule is only when the input's the base. Now our input is the. How do we start? Okay. Ryan?
B to the x plus h minus x over h,
Why are you doing that? What's that?
because x is the input,
Okay.
so you're going to put into the open form.
Open form, right? Open. We always start with open form. Start with open form. This is a legitimate rate of change function, and it will be indistinguishable from the exact rate of change function when h is small. Okay, so what can we do with this? We know we got some algebra to do here. What is the mean? What's b to the x plus h?
Well,
What's
I
it?
know that for this, you have to use ln.
Come on, it's not. No. So it's not what you remember. We're doing this from scratch, right? It's not. Oh, I remember it's this. Okay, so no. We want to understand it, so we're doing it from scratch. So what do we do with this? Just forget what you've learned in the past, Danny.
B to the x plus h is equal to b to the x times b to the h.
Okay. Because this is really saying, do what? Take b and multiply it together x plus h times, right? So we first multiply b together x times, and then how many more b's do we need? H, right? So this is how many times we multiply b together. So we can just split that up and say, all right, first multiply it together x times, then multiply it together h times, and that's the same as multiplying b together x plus h times. Make sense? Now what?
You have to go b to x out,
Okay.
like factor out.
All right, so now this is very interesting here. What are we finding about the rate of change function? What is this telling us about the rate of change function of an exponential function? What is that? What is b to the x? Yeah, it's the original function. You see this? It's the original. John Paul.
I have a question. Why would the denominator of h not be? Why would not include b to the x?
You want another h down here?
Like why would the when you factor out b to the x, why is that?
We can do it either way. I could put the h over. I could put the b to x over h, or I could put that over the h.
Okay.
It doesn't matter.
All right.
So yeah. So I pulled this h over with this because this is special in that the rate of change function has, as part of it, what does it have? The original function. You see that? So now we just have to make heads or tails of this thing. Okay, so as h gets very, very small, what will that be? What will that go to? Just b to the h will go to what? 0 or 1? 1. So therefore, the whole numerator will approach 0, and the denominator will approach. Okay, so this is essentially 0 over 0. Okay, now there's a very interesting thing about 0 over 0. Depending on the situation, as things approaching 0 over 0, there's three cases. Okay, there's three cases. It could be 0. It could be a constant real value. I mean, not that 0 is not, but just some non-zero constant. That's v for value, okay? Or it could be infinity. It could go to infinity. So those are the three possibilities for this. It's what's called the indeterminate form. This is called indeterminate form, 0 over 0. So, let's see what makes sense. All right, what if this went to 0? What would that imply? Yeah, then our rate of change function is 0. Is that likely for an exponential function that the rate of change is always 0? No, we know the rate of change is changing, right? Okay, so probably not that. What about infinity? What if this goes to infinity? Then the rate of change function is just infinite everywhere. Okay, so what would make sense would be just logically, is that this is some constant real value, some constant value. So let's take a look at it graphically and see if if the graph confirms this. Okay. So any questions? So here's the review. What we're finding with an exponential function is that its rate of change function is the original function times some constant. See that? That's what we're finding. Okay, so this is 7.5 to the x. So this is a good first example. 7.5 to the x. I've set b to be 7.5. And then I set up the open form here of the rate of change function, and I made h very small. Okay, so now I'm going to graph the rate of change function along with the original function. Tell me what you see. Can we make heads or tails of this based on what we just talked about? Here's this rate of change function. The red one's red for rate of change. Azul for accumulation. Okay, red for rate of change. So, what does this make sense with what we just concluded? Can you describe what's going on here? Patrick?
So, if x equals 0,
Uh-huh.
so then you're going to plug in 0 for x.
Okay.
7.5 to 0, so you're going to get a value of 1.
Okay.
So it crosses the y-axis.
Okay.
For f of x.
For f of x.
For r of x, you plug in 0 for x, you're going to get a 2. Or, I'm sorry, you're going to get, if you plug in, yeah.
What did we say that this function is? That we found that the rate of change function for an exponential function has essentially what form? Kyle. Original function. Some constant. All right, talk to me about 7.5 to the x. What do you think? Yeah.
It looks like it's 2 times the size of the original. So it's 0 instead of going up to 1, it goes up to 2, so the constant might be 2.
So just looking at the y-intercept here, just looking at the y-intercept there, we know it's 1 for the original function. What is it for the rate of change function? Around 2. Okay, so it's not exactly 2, but it's around 2, close to 2. So what can you say about this rate of change function here? What does it look like k is? Around 2, right? So it's showing that this, at least for the y-intercept at x equals 0, it looks like the rate of change function is 2 times the original function. So let's confirm that. I can slide up here. So let's make, around here is where the original function has an output of 1.5. So if our hypothesis is right, what should the rate of change be? Around 3. Is it 3? Yeah, you see it's crossing right there, which is around 3. What if I make the output of the original function 2? What should the output of the rate of change be? 4. Is it about 4? Yeah, so you see that the rate of change function is it looks like it's always about 2 times the original function. This is how it works. Okay, so let's do another one. So let's make b, say 4.4. Just make it 4. Okay, so here b is 4. How will we know what constant we've got now? Is it still 2? Is the constant still 2 if the base is 4? Is the constant still 2? Jessica, what do you think? So how can I kind of make an estimate of what this constant is?
I mean, looking at the y-intercepts, you can things on the graph for an x value, just
Oh, so you, okay, say it again.
ratio.
The ratio of what to what?
From an x value, the ratio of the y.
Okay, so she's saying if I take the ratio of the rate of change to the original function, I should get this constant, right? Does that make sense? So, well, I did that. Okay, so here I've set up the ratio of the rate of change to the original function, and right now I've set x is at 0. So that ratio is 1.38369. So if our hypothesis is true and I change x, what should happen to that ratio? What's that? Yeah, so for any x value, that ratio should stay the same. That would be that constant multiplier. So here we go. Ready? Watch the ratio. So here's I'm showing different x values. What's happening to the ratio? It's not moving a lick, right? So our constant k, when the base is 4, is 1.38639. Okay, next one I want to do is so I want to change this to 1.5. Okay, now the base is 1.5. What's our value of k? 0.405. If I change x, does it change? Nope. The rate of change is always 0.405 of the original function. So that begs the question, what did we have before? Before, when I did 4 and 7.5, how is it different than this one now at p equals 1.5? Those first two. So Ben, did you notice what was different about those first two from this one? Trevor, did you notice?
The rate of change is smaller.
Okay. Yeah, so now it's a fraction of it. Okay? So at 1.5, our rate of change is now this 0.4. It's like 40% or 0.4 of the original function, where before it was actually like a magnifier, right? It was the rate of change was magnified. So that begs the question. What question does it beg? Anybody?
Then b equal to 0. Constant is
Well, there is this function. Oops, sorry. What we think about is there is a function whose rate of change is what? Remember, the red is the rate of change, the blue is the original accumulation function. So we're dancing around a very, very, very special function here. Tell me about it. What's E? Who knows what that's?
The rate and the accumulation are the same. Like,
The rate, right, did you hear what she said? Allie said the rate function is the exact same function as the accumulation function. Okay? Probably one of the most special functions there is in calculus, okay? The rate function, so the amount that's accumulated so far is the same as the rate at which it's accumulating at that moment. Okay? And so that is for the value of B is here around 2.7. So what I can do is I can hone in on this and do 2.6 to 2.8 for my slider so we can get more exact here. And what am I looking at for the ratio of Rx to f of x? What am I looking for? 1, right? 1. I want to get this as close to 1 as I can. That's pretty close. I got 0.99999. Okay, so there's this number, which is approximately 2.718, and it's actually a number like pi that keeps going, such that if that's your base, when you take that thing to the x, its rate of change function is the same as the original function. Okay? Because the multiplier for this one is 1. The constant is 1. Now, before we talk about that, let's just, without showing it, this number, this constant, turns out to be the ln of your base. Okay, so the natural log, in this case, 1.3864 is the natural log of 4. So what was the first base we started with? 7.5, right? So find the natural log of 7.5. What do you expect it to be about? Remember the very first one we did? 2, right? So to find the natural log of 7.5, it should be very close to 2. Got a calculator handy? Or something? I'll just do it here. So I'll just put it in here. Natural log of 7.5. 2.0149. Okay? So let's go back to our sheet here. Push play. Okay, so this is what we found, that the rate of change for an exponential function is some constant times the original function. And I told you that constant is the ln of b, the base. Okay, so what about when they're the same function? This is this value called e. All right, 2.718. It's an infinite non-repeating decimal, just like pi. And in that case, that's the case where k is 1, and your rate of change function is the same as the original function. So this is saying the rate of change of e to the x with respect to x is exactly the function e to the x. So there it is in exact form. Okay, and so then to go along with that, so if we had something a different base, d, what's the closed form for that? So if you're taking the derivative of any base to the x, any exponential function, what is our derivative, or what is our exact closed form rate of change function? Lizzie? ln b times the original function b to the x.
So do
Yeah.
do those all mean the same thing then? Like, the bottom row?
Well, so these two, so this is the same, so we're saying this is, this derivative notation, also f prime. Well, so the prime notation, which in this case would be so e to the x prime, they all mean the exact rate of change of that function. So this means exact rate of change of the function e to the x. So our rate of change function, this is referring to the open form for any value of h. So when h is small, it's essentially equal to this e to the x. But as long as h is a finite number, it's not quite equal to it. So, did that answer the question? Yeah. So remember this is our e to the x plus h minus e to the x over h. And we're saying when h is very small, it's essentially equal to the e to the x. When you use this notation, you're saying the limit as h goes to 0, or the exact rate of change function. Okay, any questions on that? So we have another rule under our tool belt, okay, which is now we can find the closed form quickly for any exponential function. And then we know there's this very special one, e to the x. It's a very special case of that, where the rate of change function is the same as the original accumulation function. Okay. So here's what we know. Here are the two new ones we did today. And then we can also add to that, I didn't put it on here, any b to the x. Okay, just to remind you, I sent the email out. The mastery exam is not today, it's not tomorrow, it's not this week. It's next Thursday. So mastery attempt number 1, next Thursday, a week from tomorrow.
Any particular way we study for it?
Oh, well, we've got lots more to do before then. Yeah, so I'm going to give you a list of. So the mastery is basically, it's more of a memorization type idea and being able to kind of combine lots of rules. We're going to keep adding to the list of rules for Friday and Monday and Wednesday. And so we're going to have this long list of rules. And the mastery test then is being able to apply, just given any function, knowing how to apply the right rules. And as we saw with the px function that I gave you, oftentimes many rules apply in the same function. Okay? So we're going to keep adding to our rules Friday and Monday, and then like Tuesday and Wednesday it will be kind of crunch time, and it'll be like drill and practice. Just there's like a list of 100 I'm going to post. All right, and so it's just going to be drill and practice. Okay.
Can those be posted earlier?
What's that?
Are you like posting them?
I can post them. It's just that most of them at this point you don't know how to do unless you've done it in a previous class. Okay. So the first attempt is next Thursday, and so then for Friday the homework is My Math Lab online. I'm going to post that later this morning. Whenever it says derivative, what is it asking for? Which form, open or closed? Yeah, it says find the derivative of this function. It's asking for the closed form of the rate of change function. That's the meaning of derivative. Okay. That will be due Friday at 8:30 a.m. So the deadline for that My Math Lab will be Friday at 8:30 a.m.
Your water.